All right, this is going to be our walkthrough for the homework assignment titled Optimization. So these are all going to just be optimization word problems here that we're going to be dealing with. Our first one, obviously, is about a metal cylindrical container. It's got an open top, and we want it to hold 1 cubic foot. So the first thing I'll note as I'm going through here is that the volume needs to be 1, right? Our volume is 1 cubic foot. And also that this is a container with an open top, so that when I draw this, I have to keep in mind that as we talk about the amount of material, right, which is surface area, essentially, that this is open, right? We're not including that circle on the top here. So the total amount of material that we're going to use to build this can is going to be the area of the base, which is pi r squared, plus, right, because it's a circle, plus the lateral surface area. Remember that the lateral surface area, right, is the part going around. Right? That lateral surface area is always the circumference of the base, which is 2 pi r, times the height. So here is a function that represents the amount of material that's being used to build this container, right? Pi r squared plus 2 pi rh. The issue that we have here is that there are two different variables in our function, right? There's an r and there's an h, which is why it's very important that we recognize that the volume had to be 1, right? So if the volume has to be 1, that means that 1 is equal to the volume formula for a cylinder, which is pi r squared times h, right? And all of those formulas that are on the geometric formula sheet that you need to know, you're going to have to know them for all these problems. So if you don't know them, make sure you go and memorize all of those, or at least be able to find them easily enough. So we should be able to see that that means that the height is equal to 1 over pi r squared, which means I can just replace the h in my material equation with 1 over pi r squared. So we'll end up with m is equal to pi r squared plus 2 pi r times 1 over pi r squared. With a, I said plus, but I wrote an equal sign there, it looks like, plus the 2 pi r times 1 over pi r squared. So our material, once simplified, should look like pi r squared plus the 2 that's going to be in the numerator, right? And then the pi's are going to cancel, and I have r over r squared. Well, r over r squared is r to the negative 1. So here is an equation that represents the material used. Well, what we want is to have the least amount of material, which means that effectively what we want is we want the minimum, we want min material, the minimum amount of material used. So what we need to do is we need to take a derivative of this function and see when that function, when this function is at a minimum. So m prime will be 2 pi r, right? And then the derivative of the 2r to the negative 1 should be negative 2 r to the negative 2, or negative 2 over r squared. And we'll put this into a nice easy form to deal with by getting a common denominator. So if I multiply the bottom by r squared, I got to multiply the top by r squared, which is going to give me 2 pi r cubed minus 2 over r squared. Now, we know that this is undefined if r equals 0, but we're not even going to bother to worry about that because r equals 0. A radius of 0 doesn't make any sense for a cylindrical container. So really what we care about is when does 2 pi r cubed minus 2 equals 0? Well, if I add the 2 and divide by 2, we'd get pi r cubed equals 1. R cubed equals 1 over pi, or r is 1 over the cube root of pi. And so we want to make sure that that radius value actually yields a minimum. So we'll make a sign chart with 0 as the cap on our end here, and 1 over the cube root of pi for m prime. And if I plug in something more than 1 over the cube root of pi, like a billion, this is clearly all going to be a positive number. So we're going to have a positive here. But if I plug in something like 1 over 1,000, something that's smaller than 1 over the cube root of pi, 1 over 1,000 is clearly going to make this numerator here a negative, right? Because 1 over 1,000 cubed is just, it's pretty small fraction. And 2 pi times it is still going to be less than 2. So when I subtract, I'll get a negative, which means that my function does decrease and then increase, right? Because that's what my sign chart is telling me. And so I know that the dimensions that are going to give me the minimum amount of material are a radius of 1 over the cube root of pi, which we've got right here. And of course, we want our units on that, which are, looks like these are in cubic feet. So this will be feet. In fact, we'll write this on a new page since we're kind of running out of room here. Our radius is going to be 1 over the cube root of pi feet. And our height was equal to, originally, 1 over pi times the radius squared. So our height, we'll just plug this radius into that, should be 1 over pi times that radius, 1 over the cube root of pi, squared. Well, that's 1 over pi to the 2/3, which is 1 over pi to the 1/3. Or again, our height is also just going to be 1 over the cube root of pi. So we end up with the same radius and the same height to give us the minimum amount of material here for this one. For our next one, we've got an 8-foot tall fence that's standing on level ground. So I'm going to start drawing a picture here, and that fence is going to run parallel to a tall building. So here is my fence that is 8 feet tall, and here is my building, right? This is my building going up at the end here, right here. That's my building. And I think we'll label that as Y, just the height there of the building being Y. And the fence is 1 foot from the building, so that means that this is 1 foot. And buildings are going to extend up at right angles here, as is our fence. And so we want to find the length of the shortest ladder that will extend from the ground over the fence to the wall. So we want this length of ladder. We'll call it L. We've got everything else labeled in here. I'm going to just call this distance here X. Okay. And we can then use a ratio of similar triangles here, right, to note that the ratio of X to 8, so the length of this distance to the length of this distance, like the legs of that smaller right triangle, should be equivalent to the entire x plus 1 across the bottom to the other leg of y on the bigger right triangle, right? Or in other words, that y is the same as 8x plus 8 over x, right? Or if we prefer 8 plus 8 over x, whichever way you prefer to write that. Doesn't really matter. I'll probably use 8 plus 8 over x. Now, in order to find L, right, L is going to be, we'll use a Pythagorean theorem here to write this out. We'll say that L squared is equal to x plus 1 squared plus 8 plus 8 over x squared, right? That's just the Pythagorean theorem. Now, we could square root both sides of this. A little trick we can use for these is that we know that a function is at its maximum or its minimum at the same time that the square or the square root of that function is at its maximum or its minimum. So I can just basically find where the minimum or the maximum of L squared occurs rather than finding the actual minimum or maximum occurrence of L. Now, I think in the answer key I did that. I just said, all right, I'm going to deal with the L squared function, which is perfectly fine. You see that what happens if you don't do that, if you square root all of this, what you're going to end up with is effectively the same function inside of there. And so when I take the derivative of this with the square root, I get a big square root term in the denominator, but what I have to put in the numerator of that is, again, just the derivative of this, right? And so we'll write that out, right? L prime is 1 over 2 root x plus 1 squared plus 8 plus 8 over x squared times the derivative of the inside of that, right? So which is 2 times x plus 1 plus 2 times 8 plus 8 over x times the derivative of 8 plus 8 over x. Well, that's just the derivative of 8x to the negative 1, which is negative 8 over x squared. And you can see that had I not worried about the square root part, I would really just be getting this same thing here in my numerator, or that would be my only derivative. And so as I try to find out when that's equal to 0, it's going to be at the same time that this is equal to 0. So really we just want to know when does this equal 0. So we're going to have to distribute that all out, which might be a little bit of a pain here. But it shouldn't be, I don't think it'll be too horrible. Let's go to a new page for this. In fact, yeah, we'll go to a new page for this. So we had 2 times x plus 1 plus 2 times 8 plus 8 over x times negative 8 over x squared. So that's going to be, we're looking for when that equals 0. So this is 2x plus 2 plus, in fact, actually it's going to be a minus here because we got the minus 8 over x squared. 2 times 8 is 16, and 16 times 8, right, should be 128. So we're going to have minus 128 over x squared, and then 2 times 8 over x is positive 16 over x, and then with the minus 8, that'll be minus 128 over x cubed. And so we want to know when does that equal 0. And so we'll go through here and just multiply everything by x cubed over x cubed, or x, x over x, to get the common denominator of x cubed. So that'll give us 2x to the 4th for the 2x when I multiply by x cubed, plus 2x cubed. And then the minus 128 over x squared is going to become a minus 128 x, and then a minus 128. And so again, we're just looking for when this is equal to 0. So really, I only care about that numerator. With any luck, we can see that that factors quite nicely if you factor it by grouping. Right, we can factor out an x cubed, in fact, a 2x cubed from the first two terms. Right, so 2x cubed, and then that leaves you with x plus 1. And then you factor a minus 128 out there. You're left with another x plus 1 in the numerator, right? And again, we're just looking for when that equals 0, so I'm not going to bother with the x cubed part because I'm not going to have an x distance of 0. So we're looking for when does this equal 0, which would be when 2x cubed minus 128 times x plus 1 is equal to 0, which would be when x is equal to negative 1, or when x cubed is equal to 64, or x is equal to 4. And so obviously negative 1 is not going to make any sense in our problem. We're not going to have a length of negative 1. X equals 4 is the only one that makes any sense. And so if we want to find the actual length, first before we do that, we want to do a sign chart here. Right? We want to put 0 to cap that off at the end, and 4 for our derivative, right, of our length. Right? So for L prime, if I plug 4 back into my original L prime, sorry, something more than 4, like a billion, we can see, I think, that it should be pretty obvious that's going to come out to be a positive number, right? If we look at L prime, because the denominator is always positive, and if I put a billion in there for x plus 1, that's going to dominate the 8 over x and the negative 8 over x squared, so that numerator is going to be positive. And if I put in something smaller than 4, then we're going to end up with a negative number, right? I'm not going to go through all the arithmetic on that, but it does end up being negative and positive. So L is decreasing, then L is increasing. So our length is at a minimum when x is 4. And so if we want to know what that actual length is, we go back to our original length function, right? And our length function was the square root. In fact, we'll do this on a new page. Again, our length function, right? Our length was the square root of x plus 1 squared plus 8 plus 8 over x squared. And we were evaluating that at 4. So L of 4 is going to be the square root of 4 plus 1 is 5. 5 squared is 25. And then 8 plus 8 over 4, that's 8 plus 2. Right? 8 plus 2 is 10. So 10 squared is 100. This is root 125, which is 5 root 5. And I believe our units were feet here. And so that is the minimum length of that fence. All right, for our next one here, we've got a little bit of a different problem. A hotel that is charging $80 per day for a room is giving special rates to an organization if they reserve between 30 and 60 rooms. So if more than 30 are reserved, the charge is decreased by $1 times the number of rooms. So the way I like to look at these problems is if the change is only happening after a certain amount, and the change only applies to the rooms over that certain amount, or the, whatever the context of the problem might be. It might not be rooms, it might be apples on a tree or something like that. I like to call x the number of rooms above 30. And when we think about that, the total charge here, we can call it whatever variable. We'll call it c. The total charge here should always be equal to the number of rooms, the total rooms. And I'm going to write this out in words. I think that's useful sometimes. The total rooms times the cost per room, right? That should be the total cost, is total rooms times the cost per room. Well, our total rooms is going to be the number that we've reserved, right? It's going to be the number above 30 plus 30, right? So x plus 30 is the total number of rooms because we've set x to be the number of rooms. And then our cost per room is $80, but it's $80 minus $1 times the number of rooms above 30. So 80 minus x. So our cost function is just x plus 30 times 80 minus x. If I distribute that all out, I get negative x squared plus 50x. And then, what is that? Plus 200, or plus 2,400, right? Plus 2,400. That should be our total cost for reserving a certain number of rooms. Then all we have to do from there is find c prime. C prime is going to be negative 2x plus 50, right? That's only going to equal 0 when x is equal to 25. We want to make a sign chart just to confirm that, with c prime, if we put in something more than 25, like a billion, right, we're clearly going to get a negative here. And if we plug in something like 2, we're clearly going to get a positive. So the function increases, then decreases. So cost is at a maximum when x is 25. Remembering that our total number of rooms is x plus 30. So that will be 25 plus 30, for 55 rooms. So that's the maximum income or cost for these rooms. And so that's it for number 3. For our next one here, we want to find the dimensions of a rectangle of maximum area that can be inscribed in a semicircle of radius A, and we're going to have 2 vertices lying on the perimeter. So basically what we want to do is just sketch a semicircle here. There's our semicircle with a radius of A, right? So we should know that the equation of this function is y equals root a squared minus x squared, right? Because that's the equation of a semicircle with 2 of its vertices here. Not 2 of the vertices of the rectangle, but the semicircle where it's, coming down here, it's just the positive half of the semicircle centered at the origin. Right? And so if I draw my rectangle in here, right, with the 2 vertices on the diameter of that circle, or the x-axis there, we want to find the area. So the area function here, right, our area is just going to be the length times the width, right, or the base times the height. Well, our length here is, this is going to be symmetric across the y-axis. So if we've gone over x units, then our length is going to be 2 times x, right, because we've just doubled that on the other side of the y-axis. So our length is going to be 2x, and our width, or our height, right, w, is just going to be whatever the height of the function is at any given x value. So our w is just going to be root a squared minus x squared. And so our area function is going to be 2x root a squared minus x squared. And here's where a lot of people end up having some issues with this, is taking the derivative of 2x root a squared minus x squared, because they'll forget that a is just a constant. And so we're going to use the product rule. So a prime is going to be the first function, 2x, times the derivative of root a squared minus x squared. Well, that's 1 over 2 root a squared minus x squared. But when we multiply by the derivative of a squared minus x squared, we have to remember that a squared is a constant. So the derivative of a squared is 0. And so we're just multiplying by the derivative of the negative x squared, which is negative 2x. Then we'll add to that 2, which is the derivative of 2x, times root a squared minus x squared. We can cancel out one of these 2's here. So then we'll want to get a common denominator, which will be root a squared minus x squared, which means I'm going to multiply the top by root a squared minus x squared as well, giving us a derivative, a prime, of negative 2x squared plus 2 times a squared minus x squared, right? Because root a squared minus x squared times root a squared minus x squared should cancel out and just be a squared minus x squared, all over root a squared minus x squared. Right? And then if we, put this all together, combine the like terms and distribute this out and combine the like terms, we should get negative 4x squared plus 2a squared over root a squared minus x squared. And then from there, we should just be able to go right ahead and set that equal to 0. So we'll do that on the next page. We've got negative 4x squared plus 2a squared is equal to 0. We're solving for x, right? So we're going to get negative 4x squared equals negative 2a squared. We'll get x squared is equal to a squared over 2. And we'll get x is equal to plus or minus a over root 2. And obviously, we're not going to use the negative. Only a over root 2 makes any sense in this context. We do need to determine if that is a maximum or a minimum. We've got 2 options on this. One is to take a second derivative. The other is to make a sign chart. Now, it may be a little bit annoying to you to try and make a sign chart using values that are not just like regular numbers, right? It's got a constant in there of a. So if you prefer to take the second derivative, I think that's fine. It's kind of an irritating second derivative to take, but it's not so horrible. I guess we'll go ahead and do that. So our first derivative, once we simplified it all down, was, I believe, let's make sure we got this. It was negative 4x squared plus 2a squared over root a squared minus x squared, right? So we had negative 4x squared plus 2a squared over root a squared minus x squared. So if we're going to take the derivative of that, right, that was a prime. So a double prime, we'll have to use the quotient rule. So that will be the denominator times the derivative of the numerator, which is negative 8x. And the plus 2a squared is just going to go away. And then minus the numerator times the derivative of the denominator, which is going to be 1 over 2 root a squared minus x squared, times the derivative of a squared minus x squared, which is just negative 2x. And then it's all going to be over the denominator squared, right? So that'll be a squared minus x squared. Now we could go through and simplify a bunch of this down if we want to, but there's not really much of a point. I mean, I might cancel out, a 2, and to do that in a different color, I might cancel out the 2 down there with this 2, right? But other than that, there's not a whole lot to simplify. Really, all we care about is if we evaluate this at a root 2, right? What happens if we evaluate this at x equals a over root 2? Well, if x is a over root 2, we're going to see that the square root here becomes square root of a squared minus a squared over 2. And then times the negative 8. So negative 8a over root 2. For that, as negative 8 times a over root 2. And then we're going to have minus. And then up here, we're going to have a negative 4 times a over root 2 squared. So a over root 2 squared is a squared over 2. So that'd be negative 4 times a squared over 2. And then plus 2a squared. Right? And then times a negative a over root 2. And that's all over the same thing we had before, which was the square root of a squared minus a squared over 2. And of course, this is all over a squared minus a squared over 2. So now as we try to evaluate this, we don't really need to get like an actual value in the end. We just need to see if it's positive or negative. Right? And so a squared minus a squared over 2, that's going to be positive, right? This denominator here is going to be positive, so I'm going to just completely ignore that from now on. This part right here, down here in the denominator, that's going to be a positive number as well. Let's kind of like see what's going on here. So we have negative, if we simplify this numerator out, that's going to kind of be our key, right? Because we know that this number over here is negative, right? And if we subtract another negative, then we're for sure going to have, subtract a positive, then we're for sure going to have a negative. So let's see what the sign of this thing here is. This is negative 2a squared plus 2a squared. So actually this piece right here is just equal to 0. So what we've got is a negative minus a 0. And a negative minus a 0 divided by a positive is going to be negative. And if the function's second derivative is negative, that tells us that the function is concave down, which tells us that's a max. So we've now proven that we have a max at that x value of a over root 2. Okay? And so now, since the max is at a over root 2, we go back to what the question actually asked, it says find the dimensions. So if the x value is a over root 2, then the length is going to be 2 times a over root 2, right? Or 2a over root 2. Right? And the height, or the y value, the width, right? We'll call it the width, is going to be root a squared minus a squared over 2, which is just 1/2 of a squared inside the square root, right? Which is, again, just a over root 2. And so we end up with a base or length here of 2a over root 2 and a height of a over root 2. And you know, I mean, you could rewrite the top one there. 2a over root 2 is just a times root 2, but it doesn't really matter. So those are our dimensions. And the important thing to remember with that last one is that, you know, you can use the second derivative test, and you can do that for any of them. You can use the second derivative test as long as it's a place where the derivative is equal to 0, or you can make the sign chart. All right, so here we've got another one of these ones that was kind of like the hotel room one. We've got a wholesaler that's selling running shoes at $20 per pair. If less than 50 are ordered, if you order 50 or more, the price is reduced by 2 cents times the total number ordered. So this time, since the reduction is on the total number, based on the total number ordered, I'm going to let that be x. X is going to be the total number of pairs of shoes. And then we want the maximum amount of money. So we'll call it, we'll call it M for money. The maximum amount of money, or the money total, should just be the number of pairs. And I'm going to write this again in words, right? It's the number of pairs they sell times the price per pair. And I think this is easier for people with these types of problems to kind of look at it this way in terms of words first. Then that amount of money that we've got is the number of pairs, which we've just said is x, times the price per pair. Well, the price per pair, assuming that we're going to order more than 50, because that, I mean, obviously we need to sell at least 50 to get our maximum amount of money for this wholesaler, right, is going to be the cost of $20, right? That's what it was, $20 per pair, minus the 2 cents, so 0.02, times the number of pairs ordered, right? So we're getting a 2-cent discount for each pair ordered on every total pair of shoes. So this ends up being 20x minus 0.02x squared. And so as we then go through, we just need to take a derivative of this. M prime is going to be 20 minus 0.04x. We'll set that equal to 0. Right? And when we solve that, we just get 0.04x equals 20. Well, in order to solve that, we're going to have to multiply that by 25, right? So x is going to be 20 times 25, which is 500 total pairs, right? That's going to be our answer. We will prove that it is a maximum, right? In this case, it's really easy to take a second derivative, so I'm just going to do that. M double prime is equal to negative 0.04. That's less than 0, which means it's concave down, which means we have a max. Right? It shows us that it's a max. And that's it for that. For our next one here, we've got a window that is a rectangle with an equilateral triangle on top. So I'm just going to draw that. Here's my rectangle. Here's my equilateral triangle surmounting it up on top of it. We know that the perimeter is 12, and we want to find the dimensions that give us the largest area. So we have 12 feet of material to make the perimeter of this window. So I'm going to label my picture here. I'm going to call these y over here, and these will all be x, right? Since it's an equilateral triangle, right? So those all pieces of the triangle have to be the same. So our area of our window, which is what we're trying to maximize, is just going to be the area of the rectangle, which is xy, plus the area of the equilateral triangle, which you should know the formula for that. It's the side length squared. times root 3 over 4. If you don't know that formula, it's on the formula sheet, so go in, find that formula sheet, and memorize that formula. We got x and y in here, so first thing we need to do is we need to go in and convert everything into the same variable. We'll do that using the perimeter. We know the perimeter has to be 12, and that's going to be, well, everything in this picture except for this x is involved in the perimeter, so that should be 3x plus 2y, which tells us that y is equal to 12 minus 3x over 2. And so I can then go put 12 minus 3x over 2 into my y for my area equation. So I have x times 12 minus 3x over 2 plus x squared root 3 over 4 as my area formula. If I distribute this out, we end up with a is equal to x times 12 is 12x. And then if I divide that by 2, I'm going to get 6x. And then I'm going to have minus 3 halves x squared plus x squared root 3 over 4. Now, obviously, these two terms both have an x squared. They could be combined, but I'm just going to leave them as is for now because they're not. I think it's just easier to look at it to take the derivative of it this way. So a prime should be 6, and then minus 3 halves times 2 should be minus 3, so minus 3x, and then plus 2x root 3 over 4. Remember, we just take the derivative of the x squared because the root 3 over 4 is just a constant. So we'll set this equal to 0 and solve for x. So first of all, we're going to get an x is, we'll write it out in a couple of steps actually. We'll make a new page for this. So, and when we do that, we can simplify that we'll go back to it for a second. We have this 2x root 3 over 4. We can make that x root 3 over 2 as we do that. So a prime is going to equal 6 minus 3x plus x root 3. Is that what we had? Minus 3x, yeah, plus x root 3 over 2. And so now, when we set that equal to 0, we'll have negative 3x plus x root 3 over 2 is equal to negative 6. And we'll factor out the x. So x times negative 3 plus root 3 over 2 equals negative 6. Or x is equal to negative 6 over negative 3 plus root 3 over 2. And I don't know what our units were on this particular problem. I don't think we actually had, no, I think they were feet. Right, so feet for this. And we do want to confirm that this is going to give us the maximum area. So find a second derivative here, a double prime. Well, the 6 goes away. It's just negative 3 and then plus root 3 over 2. Well, negative 3 plus root 3 over 2 is certainly a negative number, which tells us it's concave down. Right? If it's a concave down function, it tells us that that's where we have a maximum. So a maximum when x is negative 6 over negative 3 plus root 3 over 2. We wanted the dimensions, so we need to find the value for y technically for this as well. So y was equal to 12 minus 3x over 2. So y was equal to 12 minus 3x. It was all over 2, I believe, right? Yeah, 12 minus 3x over 2. So if I plug that in, we get y is equal to 12 minus 3 times the x value that we just had, which was negative 6 over negative 3 plus root 3 over 2, all over 2, which is kind of annoying. But the 12 divided by the 2 should be 6. And then the negative 6 divided by the 2 should be a negative 3. And when I multiply that negative 3 by this negative 3, I should get a plus 9 over negative 3 plus root 3 over 2 feet as our y value. And so that should be our dimensions. All right, here's another one like the shoe and the hotel problem. this one, we've got an apple orchard. We've got 24 trees being planted per acre, and the mature trees yield 600 apples. But if I plant more than 24, I get less than 600 apples per year by 12. So what I need to do here is I need to write out the function that we're going to start with, which is, we want to get the maximum number of apples. So the total number of apples that we're going to use is always going to be just equal to the apples per tree times the number of trees. So what we need to do is define our variable x. So since we are reducing by 12 apples for each tree above 24, I like to make x equal to the number of trees greater than 24, because I think that makes it easier for us to write out our two different pieces of this. So that means that the number of trees that we're going to have over here at the end is just going to be x plus 24. And our total number of apples per tree is going to be the 600 minus the 12 times the number that we go over 24, which is x. So 600 minus 12x. So our function is going to be 600 minus 12x times x plus 24. If we distribute all of that out, we end up getting negative 12x squared plus 312x plus 14,400. We'll take our derivative, because that's how we determine when we're at a maximum, which gives us negative 24x plus 312. That's never going to be undefined, so all we have to do is worry about when that's equal to 0, which is when x is equal to 13. And so we have to show that this is actually a maximum. The way that we'll do that is we'll take a second derivative. So a double prime is just equal to negative 24. Since we know negative 24 is negative, that tells us the function is concave down. When the function is concave down, you end up with a maximum. So we have a maximum when x is 13. The question asks how many trees total should be planted. Well, x is the number of trees above 24. So our actual final total number of trees should be 13 plus 24, which is 37 trees. So for this next one, we are looking at a steel storage tank that's going to look like a cylinder with hemispheres at the ends. So basically we've got a hemisphere here, and then, well, that's not very good, but good enough. We've got a cylinder with a hemisphere on each end. Right? And so we're talking about the construction cost per square foot. And so we want to have a capacity of 10 pi cubic feet. So we're going to first note that the volume, which we'll come up with an equation for the volume in a second, should be 10 pi. And we want the dimensions that minimize the cost of the construction. So we know that the piece that is in the middle is going to be half the price of the pieces on the ends, right? So like the end pieces here are double, right? These are times 2 of what the center piece is, right? And so as we go through to try and come up with what the cost to build this thing is, we need to take into account the amount of material, which is going to be the surface area, but then we have to multiply the end caps of it by 2. So we've got, to do this, we've got a cost that's going to be equal to 2 for the times 2 on each of these, times the surface area of this thing. Which the surface area is going to be 4 pi r squared, because it's, if I put the two hemispheres together, that's one full sphere, right? And so we should have 2 times 4 pi r squared, and then we're going to add to that the centerpiece, which doesn't need to be multiplied by 2, but its lateral surface area is 2 pi r h, right? So this is just times 1, but it's 2 pi r h. Each of these is a semicircle or hemisphere. So each one of these has a surface area of 2 pi r squared because the full thing is 4 pi r squared if we put a full sphere together. So this is our formula for the total cost. But we need to substitute out the h. And so we need a formula for the volume. Well, the volume of this thing, which we know to be 10 pi, needs to equal the volume of a sphere. That's going to be the 4/3 pi r cubed part. And then we need to add to that the volume of the cylinder. And the volume of the cylinder is going to be the area of the base of it, which is pi r squared times the height. So we should be able to solve that for h so that we can then plug that into our cost equation for the h. So if we solve this for h, we're going to first do 10 pi minus 4/3 pi r cubed equals pi r squared h. And then we're going to need to divide that by pi r squared on both sides. So when I do that, we should end up with h is equal to 10 pi divided by pi r squared is just going to be 10 over r squared. And 4/3 pi r cubed divided by pi r squared should just be 4r over 3. We saw the minus sign in front there. So we'll take that and we'll plug it in here. And we'll end up with our new cost equation, which our cost is then going to be 8 pi r squared, and we do the 2 times the 4, plus 2 pi r times 10 over r squared minus 4r over 3. And of course, we're going to then distribute this through. And when we do that, we should end up with, we'll put this on a new page here. Our cost is going to be 8 pi r squared plus, if we look back over here, we're going to have a 20 pi r over r squared. R over r squared is r to the negative 1, so we'll have 20 pi r to the negative 1. And then we have the other piece there, this piece right here, 2 pi r times the minus 4r over 3 should be a minus 8/3 pi r squared. And we still have, now we have two terms that have the pi r squared in them, so we might as well combine those together. 8 pi r squared minus 8/3 pi r squared is going to be 16/3 pi r squared plus 20 pi r to the negative 1. And so that's the difficult part. Now the easy part comes in just taking the derivative. So we'll take our derivative here, c prime, should be, that's just the power rule there, so that'll be 32 pi r over 3, and then minus 20 pi r to the negative 2, or 20 pi over r squared. It'd be good to get a common denominator here, so we're going to multiply this by 3 over 3, and this by r squared over r squared to give us a simplified down derivative that should be 32 pi r cubed minus 60 pi all over 3r squared. And of course, that's only undefined when r is 0, which we're going to ignore. But it does equal 0 when that numerator equals 0, so that'd be when 32 pi r cubed minus 60 pi is equal to 0. We can divide everything by the pi, so those will go away. We end up with r cubed equals 60 over 32. And 60 over 32, those both will divide by 4, so that's 15 over 8. And when we cube root that, we'll end up with r is equal to the cube root of 15 over 2. And so from there, then we'll need to determine if that's a minimum or a maximum. We were originally hoping to minimize the cost, so hopefully it's a minimum. We'll make a sign chart. And so here's we'll put a 0 for the end of our r. We're not going to have a radius less than 0 or even equal to 0. we'll put the cube root of 15 over 2 here on our C prime sign chart. If we plug in something more than the cube root of 15 over 2, like a billion, I think we can see that that's clearly going to be a positive number. Right? And if we plug in something less than the cube root of 15 over 2, like, for example, 1, we end up with 32 pi minus 60 pi in our C prime. So that's a negative. And we can see that the cost is decreasing and increasing, which means we have a minimum cost when the radius is the cube root of 15 over 2 feet. So we'll say that the radius is going to be the cube root of 15 over 2 feet. Now the question originally asked us what dimensions minimize the cost. So we also want the height. So our height, and this is our radius, our height of this thing was equal to, I believe it was 10 over r squared, and then minus 4r over 3. That's what we got earlier. So if we plug in our r of cube root of 15 over 2 to this, we end up with 10 over the, we have 15 to the 2/3 over 2 squared would be 4, minus 4 cube roots of 15 over 2, and then all over 3, which is a little bit of a mess there, but we can simplify this down, I'm sure. So the 4 and the 2 should cancel. That'll become a 2. So really what we've got here is, and this 10, actually let's not do that. If we multiply, or if we do this over 4 here, that should end up giving us 40 over 15 to the 2/3 minus, looks like that's going to be, like we said, the cube root of 2 cube roots of 15 over 3. So 2 times 15 to the 1/3 over 3. If I try to simplify that down, what else can we do here with this? Seems like our best course of action is just to let's just multiply. Let's see how this works. If we multiply by the, we'll multiply by the cube root of 15 over here. So if I do 15 to the 1/3 here and 15 to the 1/3 here, that's going to end up giving us just a 15 in the denominator. So we'll have 40 cube roots of 15 over 15 minus 2 cube roots of 15 over 3. We can simplify that 40 over 15. Those both divide by 5. And this is 40. Yeah, those both divide by 5. So we end up with 8 cube roots of 15 over 3 minus 2 cube roots of 15 over 3, which we've run out of room again. We'll just drag it over here, which ends up being 6 cube roots of 15 over 3, which ends up being 2 times the cube root of 15 feet for our height. Got a little jumbled there, but that's what the arithmetic there works out to be. All right, for our next one here, we are looking at 2 vertical poles. One of them is 6 feet tall and the other is 8 feet tall. They're standing on level ground with their bases 10 feet apart. So let's just draw that. Here's a 6-foot pole. Here is an 8-foot pole on level ground. We're going to assume these are at right angles here because it doesn't quite look like I did that. They're 10 feet apart, and in fact, we'll mark that whole thing as 10. And we have a cable that comes down to somewhere in the middle from one of the tops of one of the poles and goes back up to the top of the other pole. And we want to find the minimum length of cable that can reach from the top of one pole to the ground and then to the top of the other. So I'm going to call this Y, and I'm going to call this Z. And we want to know the minimum length of cable. So we got to figure out, though, where the optimal place to put it is so that we have that minimum length. So I'm going to call this X, which makes this 10 minus X. And that gives me two right triangles that I can use the Pythagorean theorem on to then figure out what the length of the entire cable is, right? And the length of that entire cable is just Y plus Z. Well, we should see that Y should be equal to the square root of X squared plus 6 squared, and that Z should be equal to the square root of 10 minus X squared plus 8 squared. And so we can then, from there, we can see that, we just need to add those two things together, right? So our length is going to be the square root of X squared plus 36 plus the square root of, what do we end up with inside of there? It looks like that's going to be positive X squared, a minus 20X, and then a plus 100, plus another 64. So X squared minus 20X plus 164. And then we'll want to take the derivative of this, right? So L prime is going to be equal to 1 over 2 root X squared plus 36 times the derivative of that, which is 2X, plus, same thing here, 1 over 2 root X squared minus 20X plus 164 times the derivative of that, which is 2X minus 10. 2X minus 20. Yeah, I was already dividing by the 2 in my head there. So 2X minus 20. And so we could try and get a common denominator here and then solve this, but this is going to be a function that we're not really able to solve nicely by hand. So what we're going to do is we're just going to, we can simplify it first, right, if we want. It's just going to be X over root X squared plus 36 plus X minus 10 over root X squared minus 20X plus 164. And that's our derivative. We want to know when it's equal to 0. And it's equal to 0 whenever our calculator says it is. And I'm not going to go through the steps this time on our calculator. We would just graph that function and use the x-intercept function. In fact, actually what we'll do, I think, is we'll just use Desmos to do that. And so, on Desmos, we'll just type in that function, which was, you won't be able to see the whole thing I'm typing in. You'll be able to see the function, but you won't be able to see all the typing I'm doing. It's x over the square root of x squared plus 36, and then plus, and then we'll have x minus 10 over the square root of x squared minus 20x plus 164. And we can see that that function crosses through the x-axis right there at 4.28571, which we'll just call 4.286. So that minimum occurs at x equals 4.286 feet. So x equals 4.286 feet is where that wire should be put, or that cable should be put on the ground, 4.286 feet away from the 6-foot pole. And we can see that that is actually going to give us a minimum, right? Because if we look back at this, our derivative, which is what we've graphed, goes from negative, right? It's below the x-axis here, goes from negative to positive over here. It's above the x-axis, right? And so we know that that's actually a minimum, right? we can make the sign chart if we want to. Right, that our L prime goes from negative to positive, which tells us that L goes from decreasing to increasing. And it does ask us to approximate the minimum length of that cable. And so we would just then evaluate what L of 4.286 was equal to. And, well, that's going to be a little bit irritating to figure out, but we'll just use Desmos to have it do it for us. So the function that we're talking about was the square root function, right? So it's the square root to begin with of 4.286 squared plus 36. So that was the x squared plus 36 part, plus the square root of, and it's again 4.286 squared minus 20 times 4.286 plus 164, which gives us a length for that cable of 17.205 feet. And that is our final answer. And we got one more problem here to go. Now this one's a little bit different. We've got a ship that is 30 miles south of another ship and is sailing north. And then we've got ship B sailing west at a different rate. So let's just kind of sketch this picture. We've got ship A down here and ship B up here, right? And that distance apart is 30 miles. And what we've got is ship A is sailing to the north, right, at 15 miles per hour. And we've got ship B sailing to the west at 10 miles per hour. And so we want to know when the distance between the ships is at a minimum. So when is that distance at a minimum? Well, that's just going to be the distance formula again, right, or the Pythagorean theorem. So we need a function that represents the this length right here, which I guess we'll call, I'll call it x. And I need something to represent this distance, which is changing, right? It's not 30 anymore, right? It's y. So we need something to represent that distance here, which we'll call y. And so that distance x is just 10 times however long that ship has been sailing, right? So x is just going to be 10t. And y should be the total of 30 minus the 15t, however long it's been sailing. So that distance, right, our distance should be equal to the square root of 30 minus 15t squared plus 10t squared, right? And so our distance then, if we work through all of that, should end up being the square root of 900 minus 30 times 15 times 2 would be another 900t plus 225t squared plus 100t squared. Right, so our distance then becomes the square root of 325t squared minus the 900t plus the 900. And we'll then just take the derivative of this, so d prime, and we know that that denominator is just going to be the 2 root 325t squared minus 900t plus 900. That part we're not really concerned about because we're not, these distances, the distance between them is never going to be 0, so it's never going to be undefined. So this denominator, which is always a positive value, isn't really going to affect anything in the problem for us. But we will end up in the numerator with a 650t minus 900. And so we'll want to set d prime, which is that 650t. Sorry, we'll say d prime equals 0 if 650 t minus 900 equals 0, or t is 900 over 650, which would be 90 over 65, which would be 18/13 hours after they start sailing, which would be at noon. And you could, of course, break that down and figure out exactly what that time is. But, it's a little over an hour. It ends up being about an hour and 23 minutes and 5 seconds after noon. Right? So you could break that down. Figure out what, 5/13 of an hour is, right? 5/13 of an hour is about 23 minutes and 5 seconds. And that is the end of this optimization problem. Actually, what we really need to do is still, which we haven't done, is we need to make our sign chart for d prime. So we'll do that real quick with 18/13. And we'll put on something like 1 into our derivative, which gives us a negative, shows that it's decreasing, and something more like, let's say 2, shows us that it's positive, and then it's increasing. So we do know it was a minimum distance. And don't forget to do your sign chart to check that. And then that is it for the optimization homework assignment.